Okay, let's do it. Welcome to Thermodynamics, the few, the proud, the people that are here on the day before Thanksgiving that actually showed up. There ought to be extra points, don't you think? Somehow. Yesterday, we went through this refrigeration cycle, and it's in the examples. The main thing to remember is for the ideal cycle, when it comes out of the cold zone, it's at saturated vapor, and then it's isentropic up to the new pressure, and the trick is finding that point, and the only way you find it is at that pressure, find a point that has the same entropy. And then you cool it down to saturated liquid at the high pressure, and between this point and this point, what's the same is it has the same amount of energy. We don't add work. It's insulated, so when it drops, it sprays into the zone. It starts out as liquid at high pressure, maybe high temperature, and by the time it's done spraying into the low pressure zone, it's evaporated into a fog. And that's what, over here would be liquid. This is fog getting thinner and thinner until finally it's saturated vapor is not a fog, it's clear. Fog is little droplets that have condensed. So isentropic, constant pressure, and then same enthalpy is kind of the new and different thing there. So, and by the way, I just finished grading the air motor labs, and they're on the back countertop, and we'll probably go over those on Monday, sort of look at what the data shows. Last slide for this kind of Chapter 9 stuff is other ways to cool things. So, you can make the refrigeration happen with, most commonly it's done with compressor and refrigerant that does phase change. You can also do it different ways. There's a reverse Stirling cycle. There's Stirling engine. We haven't talked about it. I didn't bring out the Stirling engine. Stirling engine's a hot air engine. There's no phase change. It's a closed system. They make little toy versions of them. You can put it over a cup of hot coffee, and it runs at 1,000 RPM until the coffee cools off. And it has, well, I'll have to bring that out. Forgot about that. But you can use a reverse Stirling cycle that you can liquefy helium with it, or using helium, you can get like liquid nitrogen. It's a helium working fluid, and it does basically, it compresses on one part of the cycle, and it gets hot, and you take the heat out of that, and then it expands in another part of the cycle, and it gets colder, and it absorbs heat, and you can get the pressure difference or the temperature differences to be crazy. There was this Philips company had a laboratory scale cryogenic cooler that was a Stirling engine, and you could run an electric, like get a 12-volt electric motor and run it, and run it in one direction. It's also basically reversible. Run it in one direction until you had one end of it at room temperature and the other end was hot, like getting not exactly red hot, but like way too hot to touch. And then you turn off the motor and spin it, and it would spin the opposite direction, because now with the temperature difference, it would run backwards, and with the heat that got stored in the hot end, it would turn the motor and generate some electricity. Lots of losses, but still reversed. And then you reverse the polarity on your motor and run it the other way, and you could make it go until that end, one end is room temperature, and then the other end would go down till it was, like way cold. I mean, like way below, 100 degrees below zero or something. And then you'd turn off the motor, and it would spin the opposite direction, turn the generator back up until the temperature is equalized. And it was truly you can run those. That's Stirling engines. What they do in deep space probes, they'll have a nuclear isotope that's making heat on one end that heats up a gas, and on the other end, outer space is at low degrees Kelvin, and the air moves to the hot end, it expands the piston. Air moves to the cold end, and it contracts and sucks the system in. And there's a displacer piston that moves air from a hot zone to a cold zone, and that causes an expansion contraction. And then there's a power piston. And I don't know where my Stirling engine is, or I just whip it out right now. Anyway, Stirling engines are pretty cool. Ammonia absorption system. The ammonia absorption, the ammonia in an ammonia absorption system acts just like R134, but the way it does that is partial pressures, which we're going to kind of talk about next a little bit. And ammonia gets absorbed into water and it gets boiled out of water. On one side, when it gets absorbed, it has a low partial pressure. And on the other side, when you boil it out, it makes a high partial pressure. And the partial pressures act just like as if ammonia was the only thing there. But it's a closed system. It'll have water, ammonia, and hydrogen. And the hydrogen maintains a system pressure of like 300 or 400 psi inside the system. And net result is you take a box, you put a flame under it, and it makes ice. No moving parts. What could be simpler? Perfect sense, right? Put a flame under a box, it makes ice, right? I mean, that's all. You can also do, just take plain old compressed air. You did that with the air motor. When you compress air, it gets hot. If you have a bicycle pump and you pump it up a whole bunch, you'll feel the bottom of it gets hot. Air gets hot when it compresses. If you compress it and then store it at room temperature, the heat dissipates. And that's what happens around here. We have a compressor somewhere that has a tank that gets really hot when it's filled with hot air. It's in the basement underneath the wood shop. And then it sits there and cools off. And now you bring it through the lines in the wall that are, room temperature, and it comes out here at high pressure. Now, if you expand it, the temperature is going to drop. So that's what you saw in many of you. Like the outlet of the air motor was freezing cold. That's because that air coming to it used to be super hot. If that air had come straight out of the compressor and been insulated, when it expanded, it would have expanded back to close to room temperature. But since it was coming in at room temperature, is that expansion causes a temperature difference. And if you're starting the temperature here, it's going to go down to there. If you start the temperature here, it's going to go down to there. So you can just compress some air, cool it off at room temperature, and then expand it, and you can get, freezing cold. There's also Vortex Tube. Same concept, but it does one more step. This is one they use. There's practical application of them in cooling for, like, if you're cutting plastic on a mill, you already have shop air. These things are crazy noisy, but it basically causes spinning vortex, and it'll take that expansion, and not only as it expands, the work as it's spinning around, it also divides it into a hot flow and a cold flow. And you can get even colder air out of the cold side, and out of the other end, it takes the molecules that are moving faster. I guess I'm not sure anyone really understands how these work totally, but energy balance works, and you can get it. If you restrict the flow on the hot side, the hot temperature will get hot enough to blister your hand, and on the other side, it'll be cold enough to freeze your hand. So they'll use this. If you're cutting plastics, you don't want to get a bunch of cooling fluid and oils trapped in your plastic, smushed around or whatever. You can have one of these mounted to the machine tool, and a cold air blast that's just in that area right before the tool that pre-chills the plastic so it doesn't cut like bubble gum. It cuts like nice and sharp. There's also the Seebeck effect, Peltier effect, the thermocouple effect. I have it set up here, and I can turn it on after class, but I'll pass this around. This is a thermionic module. If you put 12 volts, well, 15 volts maximum, 6 amps maximum, it'll get a 65 degrees Fahrenheit temperature difference between the top and the bottom. Just from, normally if you pass, what happens if you pass electricity through a resistor? Does it get colder? No. Does it make a temperature difference? Yes. But it's a temperature, it heats up. It just heats up. This actually generates, one side is colder than the other side. And if you flip the polarity, it flips which side is hot and which is cold. If you've ever seen those things that you plug into your cooler that you plug into your car, a 12-volt plug-in cooler, it's got one of these in it with a fan on either side. So that's a way of cooling. There's also an interesting, I should add, vacuum cooling. If you look at your saturation curve, your saturation data, say you wanted to cool something down to 30, take a thing of lettuce. You want a box of lettuce cooled down. It just came off the field, it needs to be cooled down. You need to cool it really quickly. Well, the fastest way to cool something is throw it in the freezer, right? What happens if you throw lettuce in the freezer? Like the ones on the outside are going to turn to mush, and the ones on the inside are still going to be warm. It's not going to cool down very fast. If you washed your lettuce and then put it in the box, and then you put the box in a vacuum chamber and pull the vacuum down to the saturation pressure that corresponds with the temperature you want, the water itself will evaporate and generate the cooling. It'll absorb heat in order to vaporize, and if you force it to a pressure, it will take all of those water molecules. You'll rip them out of there, and they will take the energy with them when they go, and it will limit. You can get the core of the lettuce. It's like the pressure difference is going to cause the water molecules to come out from the core of the lettuce, and essentially it's going to find its way between the leaves, and it is going to cause it to cool down all the way to the core of the lettuce just as fast as you can pump down to that vacuum level. Vacuum level is really, really low. It's hard to do that, but they actually do that on commercial scale. I've seen a chamber that you put like 4 pallets of vegetables in, and lettuce is the best example because it's so leafy and it's temperature sensitive. But you could get it down to 40 degrees, 38 degrees, just by dialing a pressure, and its temperature won't drop below that at all. It's just going to go down to that and stay there. Now it's going to dry out the lettuce a little bit, so you do want to do it after you got it off the field and washed the dirt and it's full of water. You want to get rid of the water anyway, and you can suck it down like that. So that's a magic way of doing it using thermodynamics. So we're not going to study any of these things. But in order to talk about, this is our chapter 24 thing. In order to talk about how the absorption refrigerator works, we need to talk about some of the things that go into heating, ventilating, air conditioning, and such. So, oh, there it is. Maybe we won't have a Stirling engine demo. We talk in terms of mass and mole fractions. I'm going to talk about ideal gas and the concept of partial pressure and what that really means. What it means, relative humidity, specific humidity, and dew point, wet bulb, dry bulb, enthalpy, air mist, and cyclometric. This is all HVAC jargon, some of it. If you have a mixture of gases, you don't want to talk about the mass of the gases. You want to talk about the want to talk about the number of molecules. The ideal gas law says PV equals nRT. N is how many molecules you have. It's not how many kilograms you have, it's how many moles. And it turns out it really doesn't matter with the ideal gas law. It doesn't matter how many kilograms you have, how many, it just says N. It doesn't say that it's totally about the number of molecules. If you have helium molecule, or if you have nitrogen, or if you have something super huge, propane, mix them all together, it's still about the number of molecules, not how much they weigh. This is going to work. So, if you take the ideal gas law, PV equals nRT, and you put N equals 1 and use universal gas, universal R, 1 mole of molecules, of whichever molecules you have, will turn out to about 22.4 liters at temperature, standard temperature and pressure. If you put in the room temperature and 1 atmosphere pressure, do the numbers. And I forget if in chemistry if this is 0 degrees C or if it's 20 degrees C or 25, but 22.4 liters. It doesn't matter which thing you have. 1 mole. If you talk about a mole fraction, that's about number of molecules. And if you take this total number of moles of all the molecules and then split them up into different places, you know, how much by a number of molecules you have. That's going to be a different ratio than the mass fraction. Okay. This is a little off topic here, but normally I start this, let's see, does it go that way? No, maybe it goes that way. Yep, there we go. It's gonna pick up some speed here in a minute. It's plastic on the bottom. The plastic has to get. There we go. That's a heat engine. It's just a cup of hot coffee, right? Actually, hot water. There's a power piston. You see the little power piston in front, and a displacer piston. The area below, or the area with the blue piston going up and down, that's the air. When the blue piston goes up, most of the air is on the bottom surface, which is hot, and the air wants to expand, and when it wants to expand, it pushes the power piston. And then when the little blue piston goes down, most of the air is exposed to the top surface, and the top surface is colder. It's room temperature. And the air wants to contract, and it pulls the power piston. So each stroke on the power piston is a power stroke. And the displacer piston is just moving the air from mostly a hot to mostly a cold, and that creates expansion or pressure in an enclosed space, and that's what's driving it. Crazy, isn't it? If these are sensitive enough, they'll run like if you put it one end in the refrigerator and put the other end in your hand, it'll run off the heat of your hand. It's a temperature difference that makes it go. Okay, now that we got that distraction underway, it's speeding up, yeah? Pretty amazing how fast it'll go. Notice it's not actually doing anything. There's no power takeoff on it. It's going to basically run until the power it's generating is absorbed by the friction of internal friction. Yeah, it's an engine. I have no idea. They sell those for wood stoves that you put on a wood stove, and the wood stove, it makes it go, and then it has a fan, and the fan takes the room air, and the room air is cooler than the stove, so there's a hot end, and then it blows its own air over its cooling, and in the process of doing that, it circulates air, and it's like no electricity involved. And it's perpetual because it's not like a steam engine where you have to add water because you just blew all the steam out of it. Yeah.
Is there just not a lot of power generation with something like that? Because if you just have a really big delta T, it's going to just go faster based on.
Yeah, if it goes faster, then you can take some power off of it and slow it down. So there's you know, optimum. Deep space probes will use a version. There's something called a free piston engine, and they'll use a free piston. It's a linear engine that uses the same principle. There's a displacer and there's a power thing, and they have a coil or a magnet on the power piston as it goes back and forth, and they use that to generate power. And they have them they make them in Tri-Cities that go deep space, putting out 100 watts for the next 99 years. Because when you get too far out in the in outer space, solar energy isn't worth much. When you can't hardly see the sun when it's just another star. So they'll use that principle with like nuclear isotope and deep space temperature difference, and this linear engine that fits in. And it's a thing about that big. It's making 100 watts. Big temperature difference. More temperature difference gets you more. Eventually what will happen here, even if we kept the hot water hot, it's pumping heat from the bottom to the top because the hot air goes up and cools off, and that top gets hot, and when the two surfaces get to be the same temperature, there's no temperature difference. It won't expand and contract, so it stops. Yeah. Okay, meanwhile, back at the ranch. There's a molar mixture, number of moles of A out of the number total. That's a molar amount. Time for examples. This was one of my favorite things. Actually, that and the Vortex tubes were like my two favorite things from. We can hook up the Vortex Tube sometime, and you can see how that works. It's crazy that it works as well as it does. So here we have an example. We have 3 kilograms of oxygen, 5 kilograms of nitrogen, 12 kilograms of CH4, that would be methane. And I want to find moles, mole, I guess it doesn't without E molecules and mass. fraction. So I'll make myself a table. Love tables. Have you noticed that? Tables are like the best thing ever. So we have O2, we got N2, we got CH4. And we have a total. Got 3 kilograms, 5 kilograms, 12 kilograms. There's a number of, for mass per mole. Mass per mole for oxygen. Oxygen's 16, but it comes as O2, so a mole of oxygen would weigh 32 grams. That's a gram mole. Nitrogen is 14 per, and it's N2, so there's 28 grams per mole. This is a gram mole, is like 6 times 10 to the 23rd, it's a bucket full. And really, where it comes from, a proton, hydrogen has 1 proton, 1 electron. The electron weighs 0.794. The proton weighs 1. If you take a gram of the 6.02 times 10 to the 23rd is how many protons are in a gram, basically. And we use that number to scale everything. So for the nitrogen, we got 28 grams per mole because it's 2 times 14. What do you think for methane? Anyone want to give a guess on how much methane weighs? Yeah, 16. Carbon 12 plus 4 times 1 for hydrogen. So we'll call it 16 grams per mole. So I want to know how many moles. So 3 kilograms O2 divided by 0.032 kilograms per mole O2. I'm completely doing this by looking at units. How do I solve? So this kilograms cancels, the moles comes upstairs. And we have 3 divided by 0.032. I don't know. What do you think? Anyone have an opinion? Anyone have happy fingers? No one has a calculator. How are we going to solve that problem? Three divided by 0.3, 32, 3,000 divided by 32. It's going to be something like a little less than 100.
93.75.
How many?
93.75. Oh, wait.
Yep, I like it. And likewise, what's 5 kilograms divided by 0.028 kilograms? 178.5.
178.5.
Quite. And 12 kilograms divided by 16.
750.
Now, would you have expected? Well, this is the heaviest thing there, and it's the lightest molecule. So I guess that's not unexpected. My total mass is 20 grams, or 20 kilograms. What are these the number of moles add up to? 278. 178. 270. 1020, something like that.
Yeah, 1022.35. 1022.35.
So let's find the fraction. What's 93.75 divided by 1022.35?
Say that again. 93.75 divided by.
This is the total number of moles. This is how many of them are
10,
oxygen.
9%, 9.2%.
All right, and the next one.
Uh, 17.5%.
And 6, that's the next one's going to be like 74 or something.
Yeah, 73.5.
73.5.
I did a lot of rounding.
I'm going to call it 73.3 because it's going to add up to 100. It's going to have to. That's the mole fraction. The mass fraction would be, I can do that one in my head approximately. I've got 20 kilograms total. 5 times 20 is 100. So 3 kilograms times 5 is going to be 15%. 5 kilograms is going to be 25%. And 12 times, is that 5 times 5?
Yeah.
5, yeah, 60%. Notice the numbers are different. If this was all in a container at room pressure, call it 100 kilopascals, the partial pressures of these gases, these are all gases, if they're all ideal gases, the partial pressures are going to be proportional to this. So if it's at 100 kilopascal pressure, it's going to be 73.3 kilopascals of CH4. CH4 is going to act like, and it's going to have the enthalpy at that temperature of something that's 73.3 kilopascals. And likewise, this is going to, nitrogen's going to act like it's at 17.5 kilopascals at that temperature. Oxygen, it's 9.2 kilopascals. Because that, and you could also take that container, and if it was, say, 1 cubic meter, and you had some little dividers, and first you took all of the methane, and there's a little hole in this divider. Say that this is 1 cubic meter total, and you brought this all made this magic divider, and it had a hole in the middle of it. And you stood by the hole, and every time a methane molecule came by, you grabbed it and stuck it in the hole, and you kept sticking them through the hole until the last molecule got stuck in there. It would take up, at that pressure, 0.733 meters cubed. If this is 1 meter cubed. And then you got another divider, and you looked for all of the O2. and you stuck every O2 molecule through the hole. You'd end up with 0.092 meters cubed. And what would be left was all of the N2, and it would be 0.175 meters cubed. If you could separate them like that. So they could either have the partial volume at that pressure, or you can have a partial pressure at the whole volume. Because if this was all at 100 kilopascals, and you took this box and you sliced it and took off the two slices that were nitrogen and oxygen. So at 100 kilopascals times 0.733 times PV equals nRT. N is going to stay the same, R is the same. We're going to keep it the same temperature. And now if we expand this out to 1 meter, that's where you're going to get your partial pressure. That pressure drops to, it's going to be at 1 cubic meter, and now it's going to be 73, whatever the number was. Yeah, 73 kilopascals. So you can treat it either as a partial volume, but what's most useful is treating it as partial pressure. You can do the same thing with these other things. If I took this nitrogen, it was at 100 kilopascals with 0.175 cubic meters, and I expanded that all the way out to 1 cubic meter. P times V is going to have to equal the same. If we maintain the temperature, we maintain PV equals nRT, same N, same R, same T, so PV before equals PV after, and we're going to end up with 100 kilopascals times 0.175 cubic meters is the same as 1 meter cubic meter times 17.5 kilopascals. It acts like that pressure all the time. So there's a couple laws about that. Dalton got the law of additive pressures, which is the law of partial pressures, and Amagat had the law of additive volumes.
Do you have to start it, or will it start on its own?
Doesn't start on its own. Yeah, you have to start it. So this one's additive volume, that's the partial volume concept, and that one's the partial pressure concept. Turns out it's real. That's what makes the absorption refrigerators work. And really what we're doing is we're saying there's a total pressure and there's a total volume and there's a total number of molecules and there's a universal R and there's a temperature. And this is all about absolute temperatures and pressures anytime we're using these. For the pressure of component A, it's the number of molecules of component A on the total volume. Or you can say the volume of A is related to the partial mole fraction and the total pressure. You don't do them both at the same time. You kind of do one or the other. It turns out most of the time partial pressure is the one that we use. So, properties, and so on. Here's where it comes really, because this is what causes weather. This is what causes most of the load in HVAC systems, in the heating and cooling, especially cooling. Refrigerators don't like frost anymore. They frost somewhere, but you don't see it. Anyone ever seen like freezer frost up? Yeah, no, it doesn't. You got to be a little bit weird anymore. I mean, sometimes freezers will frost up, but used to be the freezer. You know, when I was growing up, my mom had to like every couple months just stop, take everything out of the freezer, put a pot of boiling water in it, turn off the refrigerator, and get all the. I mean, it would cake, inch thick around all the way around it, because every time you open the door, cold air would drop out, and room air would go in and it would take moisture with it. And every time you closed the door, that moisture would condense and freeze onto the surface. Your freezers are doing that all the time, but there's a cycle it goes through, and it's like every 2 days or every 20 openings or whatever it is, it goes through a cycle and it heats up and melts that stuff down. And that's one reason that it's not good to keep long-term frozen stuff in your refrigerator freezer compartment, because it goes through that freeze-thaw thing, and it's not a stable temperature in there. It'll get close to melting before it turns back on, or things on the periphery of it, especially up where the cooling coils are. But the total pressure, which is the atmospheric pressure we've been talking about, is the pressure of just the air, the dry air without moisture in it, plus the partial pressure of the water vapor. Now, you don't think of water vapor being in the air, but if I walked around here with a squirt bottle of water and just sprayed it up into the air, how wet would the tabletops get? Pretty wet. Not today. I think that if you look in the back of the room above the microwave there's a weather station, and I believe we got 10% relative humidity, or 15% interior relative humidity right now, maybe 20. And if I spray it high enough in the air with small enough mist, it'll dissipate before it comes down, and things won't get wet. It'll just dissolve into the air like salt dissolves into water or sugar dissolves into water. You can tell, you can taste, if you put salt in water or sugar, you can taste it, but you can't see it unless there's other colorings, right? And so it goes, when you have a pot of spaghetti you're boiling, there's steam coming off of it and then it disappears. Well, your room's getting more humid. And you're increasing the vapor pressure of the water. If you take a hot shower, the shower gets all steamy, yeah? Anything happen to the mirror in the bathroom? Anyone notice? Yeah, it starts to fog over. So the mirror's cold, and the partial pressure of the vapor pressure of the water, if the vapor pressure there from the steam from your shower makes the partial pressure of the water and air rise to the point where the temperature of the mirror or any other surface is colder than the saturation temperature for that partial pressure, then it will start condensing on it. Same thing in summer when there's have a glass with ice in it, it gets wet on the outside, or a can that's been in the cooler and you take the can out and you put it and it gets wet on the outside. That's not like water leaking out, that's condensing out of the air, because that temperature is colder than the saturation temperature that corresponds with the vapor pressure in the air. So if you have 100% relative humidity, that means the vapor pressure of water, the partial pressure of the water in the air, matches the saturation temperature for the steam tables at that temperature. The saturation temperature, saturation pressure related. So at that temperature, if the temperature drops, then you're super saturated. Higher pressure means you got more molecules than you can support. That's called rain. or it's called condensing onto a surface that's cold. And it's the same saturation pressure that you get on the steam tables, but the steam tables have it pretty crude down in the temperature zone that we're in. So that's, you know, I think we'll call that one good enough for today. That's what it's all about. Have a good break.